So welcome to the seminar today, and our speaker today is Marika Taylor, who is very well known, and she is now the head of the head of the Stack Center in University of Southampton. And as I already told you by email, that we are going to organize a conference together with the Stack Center of Southampton. It will be a hybrid conference and with people in person there in Southampton and all online from India mostly. So that is something that I just wanted to say and before. And so Marika today would be talking to us about fluxes and charges in de Sitter. So over to her.
Okay, so thank you very much. Thank you for the invitation to talk. So indeed, I'm going to be talking about fluxes and charges in de Sitter cosmological type spacetimes. So I'm going to start with, quite an introductory discussion of why we would be interested in this problem and, what the background is of people studying this. So as you will all be familiar with, in gravitational theories, you typically define your observables at the asymptotic boundaries of the space-time. These are the things which are the most robustly defined. And these are, of course, the things which take an important role in the context of, say, holographic dualities. Now, very commonly, these quantities are conserved charges. So, people, for example, talk about things such as the mass of a stationary black hole. But they can also be time dependent. For example, you might be looking at the flux of gravitational waves going through the boundary. And, if one thinks about the field of, gravitational physics, extensive study of gravitational charges and fluxes has been carried out really for 50, 60 years, both by physicists and indeed increasingly by mathematicians as well. I mean, the famous positive energy theorem by Yau, for example, relates to this. Now, over the past 30 years or so, the contemporary studies of charges really build on certain covariant phase space approaches developed by Wald and his collaborators. And so that's really the language in which people discuss charges and fluxes. On the other hand, in parallel to this, there has been a much deeper understanding of dealing with the issue of volume divergences. So typically one is interested in the case when one has a space-time which is infinite in some direction, so there's an issue of divergences, and deep understanding how you actually treat that has been obtained over the last 20 years or so through holographic dualities such as ADS-CFT. And one of the points of this talk is really extending this into cosmological contexts where the divergence is not in a spatial direction, but in a time direction. I should say that the relativity community typically was dealing with these kinds of divergences by doing a comparison with just flat space. That works for, the kind of problems they're interested in many circumstances, but, the way that people do it now, motivated by holography, is in a sense has some very deep conceptual insights and some, very deep elegance to it. So I've said several times holographic duality, so let's orient ourselves with just the case of anti-de Sitter. So the famous sort of cartoon on the left-hand side where the spatial slices are shown to be hyperbolic. So the conformal boundary in this case is time-like, and we interpret this in terms of a background geometry for the dual conformal field theory in one less dimension. And the charges that we define at those conformal boundary, we make them finite and renormalized using a certain counterterm procedure. So we use counterterms and we insist on certain properties that they have. They're covariant with respect to the boundary. This is, not the main topic of this talk. This is something that's very well understood by now. Now let's think about de Sitter. So the picture on the cartoon on the left-hand side is a Penrose diagram of de Sitter. You find it going back to sort of books like Hawking and Ellis. I mean, for a long time, people have known that fluxes and charges in de Sitter spacetimes have to be very subtle. So one of the charges one is usually interested in is a mass, but in de Sitter, there's no global time-like killing vector. So there's clearly no notion of mass in this sense. You have to deal with the fact that you've got compact spatial sections and the divergences are associated with, they're associated with going to the future and going to the past. So those are the sort of, the two kind of key subtleties or three key subtleties with de Sitter, which we'll be discussing today. Now, at the same time, this is clearly of increasing importance to actually understand the characterization of fluxes and charges in cosmological backgrounds. I mean, clearly it's important in the context of, inflationary models, but actually as we move into an era where gravitational wave detectors will be able to detect gravitational waves associated with, linked with cosmological evolution, linked with cosmological backgrounds. Again, one would like to understand better conceptually fluxes and charges in cosmological backgrounds. So there has been a kind of, I think, very much a return to trying to understand these issues in recent years, very much motivated by gravitational waves. So the aim of this talk is to construct the walled fluxes and charges in cosmological spacetimes, discuss what they mean. I'm suppressing a lot of the computational details through this talk, but computationally, we're obtaining our expressions using the fact that anti-de Sitter can be analytically continued to get de Sitter. So that's computationally how a lot of what we do is carried out. The talk's based on a PRL type paper which came out in December, and there is a longer version of this which is coming soon with Aaron Poole and Kostas Skenderis. And as we go through the talk, I'll link to some of the earlier approaches to cosmological charges. As I said, there's been a resurgence of interest in recent years with Ashtekar and co, Piotr Krushel, Jeffrey Compere and co, and Wald being interested in these things. So I'm going to start by sort of reminding of how anti-de Sitter can be analytically continued to de Sitter, because I think it kind of orients us on how we're going to use our prior knowledge of holography to actually assist us in the construction of de Sitter charges. So we write down a metric in the Poincare patch of ADS, probably very familiar to everyone here. So that's the ADS metric. And the conformal boundary in this case is a radial boundary where rho goes to 0. So if you take a spacetime which is not exactly ADS, but is asymptotically approaches ADS, you can define a conserved quantity, clearly a conserved mass, which would correspond to the killing vector dt. And you construct this, of course, on a surface of constant t. So that's probably the most familiar charge wall, right, that we talk about the mass associated with a spacetime. Now, how do we do the analytic continuation? Well, you basically analytically continue the curvature radius. You change a radial coordinate to a time coordinate, and then a time coordinate of ADS to a spatial coordinate of de Sitter. And when you do so, you obtain the metric at the bottom, which covers the Big Bang patch of de Sitter. So you can see now that tau goes to 0 is going to be the boundary, and this is a boundary in time, not in space. So we're swapping over the roles of space and time. And as I said, this is what people call the Big Bang patch. So it covers half of de Sitter is shaded. Tau goes to 0 is future infinity. And just as you have a Poincare horizon in ADS, here you also have a coordinate horizon at tau goes to minus infinity. As ever, you can switch coordinates, so you find global coordinates covering the whole of de Sitter. But for our purpose, I think the thing to bear in mind is that when we do this continuation, we've mapped radial infinity of ADS to future infinity of de Sitter. Now, in ADS,
can I ask some conceptual question here? So here, if you look at ADS, this conformal boundary is a place where we are putting sources and which might affect the conserved charges. And but here, putting sources would be analogous to deforming our future.
Yes.
So
and we'll come to that actually. We're going to come to that very, very soon. Yes. So yes, we will be doing that. Okay, and it almost comes directly on this slide, because as you just said, so when we do ADS GFT, we actually are very, very quickly driven to studying asymptotically locally anti-de Sitter spacetimes. So as you go to the conformal boundary, you can always write the metric in this particular form. I should say here I've restricted to 4 spacetime dimensions just for concreteness. And in this expansion, you have an expansion of a 3-dimensional metric. And in this expansion, you have 2 independent pieces of data. One is the background metric for the dual conformal field theory, and G3 that would characterize the state in the conformal field theory. More generally, you would say you have both non-normalizable modes and normalizable modes, and the non-normalizable modes are the sources, and the normalizable modes are the expectation values of operators. Okay, so G0 is the background metric, G3 characterizes the state. And when we talk about charges and asymptotically ADS, what we do is the following. We know that the holographic stress tensor is given by the G3 term. So that's the sense in which G3 characterizes the states. And if you have a conformal killing vector at the boundary, you can construct your conserved charges in terms of this holographic stress tensor. So you compute the conserved charges as an integral over the boundary of a space-like surface. So that's the formal expression. And I should say here that works even if your G0 is a generic G0. You don't necessarily need to insist that your conformal field theory is in a flat background. It can be in a generic background. You can still do this construction. You can still work it out. This map between T and the expansion of the metric becomes a bit more complicated, but you still get an expression of this nature. And this is all very well understood. Now, let's play the same trick on analytically continuing to positive cosmological constant. So on analytic continuation, we get a very similar expansion. And in fact, this expansion has been long known in the cosmology literature from Starobinsky and others. And in this expansion, again, you get an expansion near future infinity. So there are two independent pieces of data. So the Einstein equations, if you're on shell, the Einstein equations sort of force the terms in the expansion to be written in terms of G0 and G3. So there's only two independent pieces of data. And you've got two pieces of information. The non-trivial G0 actually says that you're generalizing from asymptotically de Sitter to locally de Sitter. And that is as anticipated. That's saying that you've actually changed the future. You've allowed that the future is not just, say, flat. G0 is not just flat, but it might have spatial dependence. And that will be really important for us in this talk. And then there's G3, which is a normalizable mode. And the G3 we will see is going to be related to non-trivial values of charges and fluxes. So just on formal analytic continuations, we're driven to actually say, well, we can keep a general G0. So why wouldn't we do so? As physicists, why wouldn't we do the most general case? But later on, I'm going to explain to you intuitively why you would want to keep that G0, why that's going to keep in more physics than if you actually insisted that the future is actually fixed to some specific G0, some flat G0, say. So now if we think about, the kind of differences of ADS to de Sitter, we say, the very familiar pictures on the left-hand side where time goes up vertically. What we're doing is we're thinking about computing charges on a spatial slice. We compute them at the boundary of that spatial slice. And then what conservation of charges means is that the charge is independent of the spatial slice. So we get the same answer if we're on the first slice or on the second slice. If we kind of flip this picture by 90 degrees, what should we expect? So what we should expect somehow is that we are going to be computing charges associated with time-like slices intersecting future or past infinity. So that's what's shown, T and T primed. So we're computing something on T primed. And then a notion of conservation is going to be that when you make a spatial displacement, so you move across T prime to T, that you actually get the same answer. Okay. Now, you might find that a little bit puzzling or a little bit different, but remember what I said at the beginning, that we really didn't expect, we know that in de Sitter, we don't have, say, a global time-like killing vector. We know that spatial sections are compact. We know that the things, the divergences are in time. It's kind of, this is what we would, in a sense, expect as a sort of framework for setting up our charges. So we're going to be computing things on time-like slices. And then we're going to be asking whether they change under spatial evolutions, so when we shift this surface to, spatially. Okay, now I need to, introduce a little bit of the background of the covariant space-based formalism, which is, for those who teach or study, phase space in undergraduate will be in some sense very familiar. For those who haven't seen it for a while, it can look a little bit formal. I'm going to sort of, put the very minimum of what we actually need just to give you a sense of how these constructions work. So here's the key quantities. I should say for anyone who's been working on things like, entropy and higher derivative theories, I'm sure you're very familiar with the world formalism and it will be straightforward. So we're interested in a situation. I should have said earlier that although for the most of this talk, I'm just doing Einstein gravity with just a cosmological constant, pretty much everything I say here could be generalized to have, higher derivative gravity theories, also to have different sort of fields present. So there's no problem with this. It's just for simplicity, we just keep at first pass to just having the, just Einstein gravity with positive cosmological constant. So here we're a little bit more abstract than that. We say that we've got a gravitational theory, which is described by a Diffie covariant Lagrangian. And in general, this depends on fields which are not just the metric, but other fields too. Then, given this Lagrangian D form, and it's convenient to work in terms of in the language of forms because we're going to be integrating these things over, different surfaces. So on-shell variations can be expressed in terms of the exact derivative of as an exact derivative expressed in terms of a symplectic potential D-1 form. Okay. So, just to orient you, if you were writing this down just for Einstein gravity with cosmological constant to get a form, you're really just, taking Poincaré dual, you're just basically writing down the sort of volume form, right? So the overall form of the Lagrangian D form is just the familiar thing that you're used to. And as I said, I just said it's straightforward if you want to add in additional fields, so you can do FRW spacetimes with scalar fields present, no problem. Now, if you want to compute the symplectic potential, that's simply a computational exercise. And if you do it for the case that I've given over here, this is something that we would often do in first courses on general relativity when we're discussing the sort of variational problem for general relativity and the derivation of the Einstein equations from an action. You can convince yourself, fairly easily that the symplectic potential can be written in this form in terms of the covariant derivative of the metric variation. So again, we're not going to use this expression in detail. It's just to give you a sort of a brute force explicit form for it. Now we need another generalization that is built out of theta. So this is and this is perhaps the form that we use the most extensively in the discussion. So it's the symplectic current, which is a D-1 form. And you get that from an anti-symmetrized variation of theta. So you consider two variations, delta 1, delta 2, and you do, as I've shown here, this anti-symmetrized variation. So a particularly crucial property of omega, the symplectic current, is that it's closed on shell, right? And that's something that we'll be using. So we'll be working on shell and it's closed. And because it's closed, that means that you can do all kinds of manipulations with it in formulae. Now, how does omega relate to what we were trying to do, which is we were trying to construct, we're trying to discuss charges, we're trying to discuss fluxes. So if we're going to start trying to discuss these, we need to we need to define them with respect to some particular vector field. So let's start with a diffeomorphism generated by a vector field. So that's not, for now, let's not assume that this is associated with some kind of symmetry, that it's a killing vector. Let's just be more general than that and consider just a diffeomorphism which is generated by a vector field. So then we can define a Hamiltonian in a broad sense. I think sometimes one has, people mentally want to think of the Hamiltonian as the thing that's associated with a symmetry. You really want to think of it as associated with a conserved mass. No, this is a more general Hamiltonian. This is a Hamiltonian that's associated with this particular diffeomorphism. And this is the quantity that you get by integrating your symplectic current, where the variations here are the variations of the field itself, and then the Lie derivative along the vector field of the field. You integrate this over a D-1 dimensional slice. Now, I put C here, and I use the terminology C because for many applications, this would be a Cauchy surface. So if we were just in 4 space-time dimensions, C is 3-dimensional. So it's actually, just a spatial slice. And so we're integrating over that spatial slice. But for our purposes, it's important to be general. Yeah.
Marika, can I ask something? So here, since omega is closed, it is also assumed it is exact.
It's going to be locally exact. You have to be a bit careful.
Locally exact. And yes. So H should be well defined over the
Exactly. So we will use this quite heavily in just a moment, actually, this point. Okay.
Okay.
So indeed, this comes in just a moment. So this is the Hamiltonian. So this is a sort of very general construction, as I said, because right now we haven't insisted that our vector field is a symmetry, right? It's just a diffeomorphism generated by a vector field. Now, for any such diffeomorphism, we can also define something, define a Noether current. And again, I emphasize, whilst we're used to the fact that Noether currents are used in the sense of the vector field being a particular symmetry, here we're actually using it just for a diffeomorphism rather than a killing vector. So we construct this. This is the formal form. So it's written in terms of theta, and then it's a contraction of the vector field with the first index of the Lagrangian D form. Now, by construction, this thing is closed on shell, and that's why it justifies the name of the current, right? dj equals 0 on shell. And that means that it's at least locally exact. You can always write it as a dq, where q is a d minus 2 form. So this is just, a writing, a formal sort of writing of, Noether currents and Noether charges in this context. Now, the Hamiltonian that we defined just before, if you do a variation of this, this can be, written in terms of something which is integrated over the boundary of our surface C. So if we just for concreteness go down to, is this just on 4 dimensions? Our C was 3 dimensions. DC is 2-dimensional. Okay. So by construction, we can just manipulate the formulas we've been using and write the variation of the Hamiltonian like this. You can integrate this equation up to obtain the Hamiltonian if and only if the second term here is itself a total variation. So clearly that's already written as a variation, right? But in general, this is not necessarily written as a variation. So you can integrate the equation to get your Hamiltonian, if and only if you can write it in this form. So you must be able to express it as delta of something. And it turns out that kind of, requiring that you are able to do that is an important kind of constraint on important way to understand the nature of these walled Hamiltonians. Now, we also anticipated that we would be wanting to think about how our Hamiltonians are conserved, how our Hamiltonians change as we go between different slices. So you can straightforwardly show that the difference between the Hamiltonians on 2 different slices is given in terms of the integral of omega over a hypersurface whose boundary is the boundary of the 2 C's. Okay, so that's, again, I'm going fairly fast through it, but these are all things that people know, and they've proven, and it was proven back in Wald's papers in the early 90s, and it really goes back to the sort of foundations of sort of phase space and Hamiltonian theory. Now, this expression, I think, is probably the one that's the most useful to think of in terms of the talk. So even if you forget about the details of the definition of omega going forwards, it's really that this quantity, the omega, that you construct in terms of your Lagrangian, in terms of the vector that defines your diffeomorphism, that this omega plays an important role. And you can see why it is by looking at this equation, because clearly it's the case that your Hamiltonians are independent of the slice you chose if omega is equal to 0, right? That's definitely a sufficient condition. And in most of the situations, you could say, well, maybe it's the case that omega is non-zero, but the integral over b1, b2 is 0. Of course, that can happen too generically, but in most of the situations we're interested in, it's actually the case that omega itself is just 0 over all of b, right? And then that guarantees that the Hamiltonians are independent of the slice. Okay, so if you're looking at conservation, omega plays an important role. Now, that's the sort of formula that we're going to sort of talk about as we go forwards. But let me now come back to the picture that I showed you before and remind you that I've been quite agnostic about the nature of my slices. So in the ADS case, as I said, that you were thinking about a 3-dimensional spatial slice, and DC would be the boundary of that slice, right? It would basically be the sphere at infinity. And then the statement that we have on the previous slide here, what would be B1, B2? Well, it would be the thing that I showed, is shown in gray in this picture, right? It's basically the cylinder. So the cylinder, the top ends on the top slice, the boundary of the top slice, the bottom of the cylinder ends on the boundary of the bottom slice. So what we're basically saying in the ADS case is that, our Hamiltonians are conserved if our omega actually is 0 on that conformal boundary. In the context of de Sitter, we're going to have to be a little bit more careful, and we'll pull that through in the coming slides. But just to sort of start us off on what we expect to be happening, the slices we're going to be interested in are these time-like slices, right? So this is the thing which is shown vertically. So that's our three-dimensional slices. The boundary of this, well, I've kind of already anticipated that there's something subtle happening in the interior, but there's certainly one boundary where it touches conformal infinity, right, where it intersects with conformal infinity, okay? And then the question about, are things independent as you go from T prime to T? Well, that's clearly going to be related to this thing here, right? This part of the conformal boundary. So if our omega vanishes up here, then we should also have things being independent and not depending on whether we're on T primed or on T. Okay, so it's again just showing you the pictures to say you're basically tipping everything by 90 degrees, right? Where something was space-like, it's now time-like. Okay, so it's really, this is a space-like, it's part of the Scri plus future infinity, and our questions will be whether our omega actually vanishes here, and if so, we're going to have conservation of our Hamiltonians between the two slices.
But Marika, I just wanted to ask, so here, when you're talking of a symplectic evolution or symplectic language, you're talking of this evolution in spatial direction, not really in time.
Yes. And I think it's important to, to note actually that whilst the vast majorities of our discussions are in situations like this, even when we do flat space, even though the boundaries are actually null, we're almost always foliating it in terms of spatial slices, right, and doing time evolution of that. So we're almost all our discussions in the physics literature on this. But actually, if you go back to Wald's papers in the early 90s, Wald and his collaborators, it was completely agnostic about the nature of C and partial C. So it could be null, it could be, it could be space-like, it could be time-like. Okay, so. I'm emphasizing this a lot. I mean, in the last few years, I think people have appreciated this to some extent in the de Sitter case. We have some new things to throw in, which I'll bring in through the talk. But it's sort of really the fact that this is the natural thing to do in de Sitter is to really put it as time-like slices. Okay, so now let's talk about asymptotic symmetries and charges first in ADS. So in asymptotically ADS, we're usually interested in things which are associated with asymptotic symmetries. So in particular, we've got some kind of killing vector at the boundary. So we've got, in the context of ADS CFT, the CFT lives on a background which has got a symmetry. And so then we've got, we have in the bulk ADS something which is asymptotically a killing vector. More precisely, it's a conformal killing vector, but that subtlety is not particularly important for our purposes. So if I kind of write it down, so I said, that, we've got an asymptotic form for the metric like this. It just turns out technically it's slightly easier to relabel my radial coordinate rho as e to the minus r. That's just a sort of, technicality. Then, my conformal killing vector has, my asymptotic conformal killing vector has particular properties. And the point here is that we can express it in terms of zeta, which is a conformal killing vector of the metric in which, the G0, the boundary metric of our spacetime. And as I've sort of alluded to already in the previous picture, but now let me, take it as less of a cartoon and a bit more precise. In the case of ADS charges, what do you do? So you work on a spatial slice, which is shown in red. And then, the question of integrability and charges being independent of the slice, that really turns into a question about how does omega behave on the section of the conformal boundary that links the two spatial surfaces to each other. And that's shown in green, just to highlight it explicitly for you. And in fact, you can show that this is automatically satisfied. So if you're just working, so we're working just with Einstein gravity with cosmological constant, you can just do brute force calculation. You've got particular boundary conditions on the metric, right? So you can just do the brute force calculation and show that this is 0. In the case that you've got a conformal killing vector of G0. So, you're working with a vector such that this is an asymptotic conformal killing vector. It's just 0. So this means that the charges are independent of the choice of slice. Now, in recent times, sorry, before I go on to that, so again, your favorite charge that you would be calculating is usually something like a mass or an angular momentum, right? So you have a stationary space-time, and you're computing something like the mass and angular momentum. Now, of course, in recent times, people have considered, much more interesting and complex dynamical situations in ADS, particularly when they're doing numerical evolutions. And so you may be interested in a situation where you have gravitational radiation. Now, when you have gravitational radiation, and that's shown in green in my diagram, so that's moving at the speed of light and hitting our conformal boundary, passing into the conformal boundary. The gravitational radiation reaches the conformal boundary in finite proper time. And with that kind of fluxes coming through, the boundary conformal structure is time dependent. And so at most, you can have piecewise constant charges, right? So, another way of sort of saying it is, I think it's intuitively quite straight, quite obvious. And it's this kind of phenomena is discussed quite a lot in recent discussions of asymptotically flat space-times and so on. It's clear that, as that flux kind of hits the boundary, that, things are going to jump, right? And so at most you could have piecewise constant charges. Now, this is a more esoteric, a more exotic situation in ADS, but clearly in the de Sitter case, this is not such a sort of a strange thing to be happening, because we're really thinking in terms of cosmological backgrounds. We really do expect to have, phenomena where we're generating gravitational waves. So we've really got to think about what's going to happen when we've got gravitational radiation flux in our spacetime. So now let's move to de Sitter charges. So again, we're playing the same kinds of tricks. So let's consider first the situation where, again, our boundary metric at future infinity has a killing vector. Okay, so just analytically continuing the expressions I had before, we get exactly the same kinds of structure, but now we're working with the conformal killing vector being the conformal killing vector of future infinity. Now, compared to what we have, what has been done previously, this is a point where we really go beyond the past literature, because our analysis applies to space-times which are asymptotically locally de Sitter, not just asymptotically de Sitter. So almost all the prior literature on the subject, much of which comes from mathematical relativists as opposed to the more string community, but people like Ashtekar, Krischel, and co., really assume that G0 is flat. Okay, so they fix the G0 and they assume it's flat. But that's something which is unnecessarily restrictive in the sense that we can do the calculation for any choice of G0, right? Any non-degenerate choice of G0. And this is the point where I sort of point in and say, well, why would we want to allow G0 not to be flat? And that actually kind of links back neatly to what I was just saying about ADS. So we said in ADS that as the gravitational radiation hits the conformal boundary, clearly, there's time dependence there, right? The G0 wants to be time dependent, okay? The analog of that in the de Sitter case is that if you have gravitational radiation present in your space-time and radiating out to future infinity, the G0, the metric there, has to be spatially dependent, right? So as the radiation comes and hits it, the metric has got to change, once the gravitational radiation has hit it. And again, I would argue from a physical perspective that you would want to allow that, because if you assume that that's not happening, you've basically switched off your sources of gravitational radiation reaching the boundary. It's just too restrictive. Okay, but having said that, let's go back. I mean, as physicists, as we always do, let's do first the simpler, more symmetric case, and then let's generalize it. So let's consider first what happens in the symmetric case where G0 is just flat. So in the asymptotically ADS case, if you take G0 to be Minkowski, the boundary metric is just flat. The symmetries are the usual ones, right? So it's the usual conformal group of the boundaries. You've got time translations, root boosts, and rotations, and so on. If you analytically continue into the sitter, you've now got a boundary metric which is Riemannian signature. G0 is just the Euclidean metric. And so the conformal symmetries you're interested in, you don't have, of course, a time translation because it's a Euclidean metric. You've got spatial translations, you've got spatial rotations. And now, because we're interested not just in the symmetries, but also the conformal symmetries, you've got a scaling transformation as well. Okay, so this is the analog of the dilatation symmetry that you would have in the ADS case. So those are the symmetries. And if we just pause there, that already tells us that we will, even in the case that we're looking at asymptotically de Sitter, and now we're trying to construct charges which are associated with the vectors generating these things, we're not going to have a mass because we don't have, we simply don't have a time-like killing vector, right? We're going to have charges associated with each of these things, including our scaling transformation, but we're not going to have something which is, which is a mass in the same sense as we have when we have got a conformal boundary which is time-like or null. That doesn't mean, so we're going to define something which is very much analogous to a Bondi mass, but it's not going to be a mass in the sense in the same sense. Now let's think about the surfaces. So here I'm sort of, starting to orient us with what would be the particular choice of a vector with which we would want to define our charges. And so in the case that we've got just a flat boundary metric, these are particular, these are the natural things to construct charges with respect to. The next thing we need to do is think a little bit more carefully about the surfaces. So if we rotate from ADS, we've already said several times that the surfaces are time-like. I switched notation here. Now we're just focusing on de Sitter. Let me just call the surfaces on which I'm going to integrate to get my charges. Let me call them C. They're time-like. But now we have to be a bit more careful because, we've been talking about how that surface intersects y plus. But actually, we've got to kind of, extend it into the past in the space-time. And we've got to worry about, the fact that it would have another end as well. Okay, so now this doesn't come into play in ADS. So, it can come into play, but usually it doesn't come into play. And I'll come to that in just a moment. So in ADS, you could say, well, actually, when we take our spatial surface, why was it that actually, why was it that there was no inner boundary there? Well, usually the fact is that, you have no inner boundary of the space-time, and also typically your fields die off. You've got regularity conditions on the inside, so actually there would be no contributions, even if you do have inner boundaries. In the de Sitter's case, you really have a boundary at the future and at the past. So in the picture, I've shown one end of the surface at Scri plus, and then I've given a slice at finite t, and I could choose my slice to be, I could choose my region of interest to be the shaded region. Of course, I could also think about surfaces that extend all the way between future and past infinity. And there's nothing wrong with doing that. My coordinate system my Big Bang coordinate system doesn't cover all of that space-time, but I can choose cleverer coordinates so that I can actually cover all of the space-time and actually get from future to past infinity. So suppose we're in just de Sitter, pure de Sitter itself, or perturbations of de Sitter. Let's choose such a slice that goes between future and past infinity. And suppose we're looking at a vector, bulk vector, which is an asymptotic conformal killing vector in both future and past infinity. Okay, so basically this would be satisfied, for example, if at scri plus and scri minus the metric was flat, and then we could pick one of these conformal killing vectors of the flat metric, and that could be that extended in the bulk could be the thing we're interested in. Now, in this situation, really by directly continuing the calculations from ADS, we can show that our integrability criterion is satisfied. And so that the charges, the Hamiltonians that we construct on C1 are independent of the slice that you choose. So C1 is the Hamiltonian, C1 is the same as that on C2. Another way of saying it is that the omega on B plus and B minus, so the blue line shown in the diagram, are automatically 0. So how do we actually do that? Well, again, we are just using the asymptotic expansions of the metric and the momentum, and the integrability condition is satisfied if the vector we're working with is an asymptotic conformal killing vector, and if the momentum, so the expansion of the momentum near past and future infinity, actually is traceless. So the third term in the expansion is traceless. Now, I'm suppressing, sort of technicalities and computations here, but I wrote that specific formula because it might be familiar to some of the people here. This condition in ADS is exactly equivalent to the fact that the conformal anomaly vanishes in a three-dimensional CFT. So it's the same thing as the fact that the trace of the stress tensor is 0 in a 3D conformal field theory. There's no conformal anomaly. And so it's just directly inherited analytically without being, being completely agnostic about whether there's a meaningful quantum field theory dual to four-dimensional de Sitter. I'm agnostic about that. Just computationally, when I just manipulate the Einstein equations and do the analytic continuation, it's automatically the case that this term vanishes, and hence that we inherit a conservation of our charges. Okay, so let me just flip back here. So let me repeat again the statement. The statement is that if you've got something which is a killing vector at both future infinity and past infinity, then the charge will be computed on a time-like slice here will be independent of that slice. We will be able to show that what we get on this slice is the same as what we get on this slice.
Marika?
Yeah.
So does it mean that the Ricci scalar of the two boundary metrics, that the spatial metrics at future and past are 0? So
I haven't quite been as restrictive as that, because I'm still not assuming. I'm assuming that I've got a conformal killing vector. I could have a non-trivial curved metric, right? So in particular, it can be a sphere, right? You can compactify. When I say I can compactify my flat metric to be a sphere, and so that would have a non-zero curvature, right?
Right, but in 3D CFT, the conformal anomaly is simply proportional to the radius of, to the Ricci scalar of the. Not
in a 3D CFT, right? That's the 2D CFT.
So that's 2D, yes, sorry. Yeah, the 3D, of course, is 0, of course. Sorry,
it's 0, yeah.
Sorry, you're talking of the 3D here, sorry. Yeah. Okay.
So it's the 3D boundary, the bulk is 40, yeah. Okay. So, so we've said that we expect that the expression to be independent of the slice. So let's just give explicitly what the expression is. So if you've got a time-like slice with boundaries at scri plus and scri minus, you can write your Hamiltonian in terms of the contributions at scri plus and scri minus. And these have really analogous forms to what you have in the ADS case. So the contribution at scri plus is written in terms of T, what we call T plus, AB, which is basically the third term in the expansion, in the asymptotic expansion of the metric. Okay, so we get these two contributions. So the important thing here, just to emphasize, is that, because our slice has two boundaries to it, we're, again, very used to the fact that when we compute a charge, that we take the contribution from infinity. But here, we've got two infinities, right? The future and the past, and that's why we get two contributions to the charge, right? And the sign just comes from, the orientations. I mean, it's just the usual thing.
So just one So this is guaranteed already by the equations of motion that this.
So this is guaranteed. This is guaranteed. We're always on shell
Right.
here, so it's guaranteed by the equations of motion. Yeah. So
Motion that pi3a, the trace of pi3 will vanish.
The off shell pi3 would not vanish. It would not be restricted because we wouldn't. Yeah. So we're
on
really
shell. On shell.
We're really on shell. Yeah.
And but if I did the same procedure as you said in say in 5-dimensional DS, then we would have this. We have to restrict the boundary metric appropriately.
Well, if we had that, we'd have to be careful about conformal anomalies, but there would be a whole analogous story just as there is. So you'd have the fact that you have anomalous transformations of your charges associated with the conformal anomalies, but it's just in fact the same mirror story that you get for ADS and other dimensions. Yeah.
Okay.
So you get this expression for the Hamiltonian associated with your killing vector, and indeed, as we said, you can explicitly show. So actually, I said that the whole expression was going to be independent of the slice, but actually you can refine that. It's in fact the case that the contributions from scribe plus are independent of the slice. So the difference in the contributions at scribe plus between C1 and C2. So you're computing one here and comparing it with one here, that's 0. And similarly at scribe minus. Okay. Now, in fact, if you have a space-time which has got an asymptotic conformal killing vector at both past and future infinity, you can in fact prove something even stronger. So that's a pretty restrictive condition. So again, if we think about physically and intuitively what it's happening, is it's basically saying that there's a symmetry of our metric across all of scribe plus, across spatially across it. It's really strongly precluding you having gravitational radiation, because if radiation was coming, it would be disrupting the symmetry, right? So if radiation was coming and propagating through the space-time and hitting scribe plus, you wouldn't be able to have these symmetries. So in fact, for solutions that have the symmetries at both past and future infinity, you can show that actually if you choose any Cauchy surface, any time-like surface, IT, and you think about charges which are defined in this box region here. So just between scribe plus and IT, you take your inner boundary to be there, not all the way to scribe minus. It's nevertheless true that the contributions to the charges at this surface don't depend on whether you're on C1 or C2. Now, in terms of how this compares to previous discussions of charges, the previous literature has almost always implicitly assumed that the contributions just vanish. So they've done it through imposing fall-off conditions in the interior. That's what's happened, say, in the Ashtekar-Krichiel kind of work. Often people are working in linearized gravity. So they're, say, taking de Sitter, and then they're putting a linearized field on top of de Sitter. But these, the conditions that they impose here are really unnecessarily restrictive, in the sense that you don't need to impose that. And it's also not physically reasonable to insist on making your fields fall off. You lose physical situations. Okay, so in our discussions, as I said, in this specific example, we are able to prove properties of the contributions to the charges from IT. So when we compute the charges, we get contributions from both the future boundary and the past boundary. We can prove things about these, but we're not just assuming that these are 0. The past literature just assumed that all these contributions would be 0. Now, if the contributions from this surface actually vanish, which happens in some case, then you get a particularly neat form for the whole charge. So you only get a contribution from infinity, and it really looks completely analogous to the expressions from ADS4. Okay, so in ADS4, you just get the contribution coming from radial infinity. It's really exactly the same. Okay. But again, we don't in general insist that this is the case. In general, we will have contributions not just from future infinity, but also from the past boundary as well. Now, In the presence of radiation, this is sort of a more interesting case. Our vector is no longer an asymptotic conformal killing vector. So this is, you can see this in the picture, why you would expect this to be the case. So the gravitational radiation is shown in green, and you can see that it propagates out there to Scri plus. And when it hits Scri plus, you've got a pulse of energy hitting, right? And you would say that actually that has to disrupt the symmetry. There's no longer a conformal killing symmetry. And you can show that, that there's this, just by Stokes's theorem, basically, that, the changes that you get between delta Q plus now differs from delta QT by the amount of radiation in the region. So, when we no longer have the case that the charge is computed at the boundary of C1 is the same as the boundary at C2. That amount sort of differs according to the amount of radiation you have in the region. And there's a particular expression that you can write in terms of that, and an analogous expression for delta QT. So, I'm not going to give you the particular detail of this, but you can actually see that there's, you're measuring the change in your charges, your contributions to the Hamiltonian in terms of the flux that's coming through your box region. So to give you a sense of what this means, rather than just going through the formula for the flux, let me actually give you some physical examples in the last few slides to give you a sense of what these things mean. So we'll build it up case by case. So if we write global de Sitter in 4 dimensions, this is a form of the metric which might be familiar to some of you. And if we're looking in the future patch, then R is greater than this value. This is the position of the horizon. You can sort of, work out in this case for any of the asymptotic conformal killing vectors. So this is just global de Sitter. So the metric, the boundary metric is trivially symmetric. But for any of the asymptotic conformal killing vectors, the charges vanish. So this is, I guess, what one would expect. This is in the sense the ground state of the system. This has got just 0 charges. So the next case you'd go to is, okay, well, the next simplest thing to do is have Schwarzschild de Sitter. And again, if you write the metric in the future patch, it can take this form. So the difference here is the term here. And this fits into the framework that we were just discussing in terms of having asymptotic conformal killing vectors, because you've got no gravitational waves in this space-time. So you don't have a global time-like killing vector, but you certainly do have asymptotic conformal killing vectors. If you want to sort of think about the region that we're in, you might want to go back to sort of, the pictures of the Penrose diagrams of Schwarzschild de Sitter. So we're really sort of working in this region, and you can think of us, the kind of boxes that we're using, the kind of time-like slices as being these blue lines. And what we're saying is that, we would be computing things in one of these slices, and it should be independent of the slice. So if we move to the next slice, we will get the same answer. So if you kind of do the computation, so in particular, if you just move to Pfeffer and Graham coordinates in near Scri plus, you can, extract the non-trivial G3 term, and perhaps unsurprisingly or inevitably, this term has to be proportional to the parameter in the metric M. Now, the non-trivial charge here is associated with the scaling transformation. So, there is a non-trivial charge which is proportional to M. I emphasize that this is not a charge associated with a time-like symmetry. So in a sense, the notation M is a little bit conceptually misleading, right? Because it's not associated with a time-like symmetry, it's associated with a different symmetry. But nevertheless, as we'll see in a moment in a sort of non-trivial example, the kinds of things that you'd like to see in terms of monotonic behavior, monotonicity behavior of a Bondi mass is nevertheless seen with this particular charge. Now, all the other charges are trivial because this is a symmetric space-time, right? So by, Schwarzschild is symmetric. We didn't break rotational symmetry, so the other ones are trivial. If you want to kind of get something non-trivial for the other charges, well, the obvious game to play is you go to Kerr-Nutt de Sitter solutions, which are a 3-parameter family of solutions. And then you get non-trivial charges, which are expressed in terms of these parameters. So let me, in the final few minutes, kind of conclude with a more complex example. And it's more complex because this is something where you've really got gravitational waves and real dynamics going on. Now, it turns out that, it's, particularly nice, case study for this is a well-known family of exact solutions that go back to the relativists Robinson and Chapman. So they're a very generic set of solutions which are known with cosmological constant and without cosmological constant. So this is the form for the metric. As I said, they look a little bit scary at first because you have to define the solutions in terms of functions which solve particular equations. So you define the solutions in terms of a function p and a function phi, which is constructed from p. And there's a sort of a defining equation here, a differential equation for p. And so this, this is sufficient so that this solves the Einstein equations with cosmological constant. And in fact, you see that the cosmological constant actually only comes into the reconstruction of the function phi. The actual function p is independent of the cosmological constant. Okay, so this looks a little bit, looks a little bit messy. The point is that actually, if you take your function p and then reconstruct from it, phi, and then the rest of the metric, then for a suitable choice of p, you can solve the Robinson-Chapman equation. And so, you can choose a general function p such that it solves that differential equation and it asymptotes to Schwarzschild de Sitter at future infinity. And how you interpret that physically is that that's something which is settling down, which is kind of relaxing to become a Schwarzschild de Sitter black hole. Now, why is this an interesting test case for us? Well, the point is that if the defining functions p have a non-trivial u dependence, so if I just flip back on a slide, so if I solve for, if I take a trivial solution for p, you can kind of play a game to convince yourself that this really just does give you exactly Schwarzschild de Sitter as we had in the previous slides. And here dz bar is just the metric on a sphere written in complex coordinates. But if I take a solution which has got u dependence, u is really a kind of a null coordinate, then I've got a non-trivial solution in which I've got gravitational waves present. So it's just for us, it's a nice kind of test example. If I kind of try and draw a little picture for you to give you a sense of what's going on, just concentrate a little bit on the top right region. So what we're saying is that up in the top right region, it's asymptoting, so it's approaching Schwarzschild de Sitter, so just the Sitter black hole, but then there's gravitational waves which are coming through, which were produced back in the earlier times in the space-time. And so you can see that when I choose my sort of box region, so I'm going to be choosing, trying to define my charges on the red slices, and I'll be asking questions about how do they change between the left red slice and the right red slice. You can see that this is a case where if there are gravitational waves present, the gravitational waves are coming through the boxes, and we clearly do expect things to jump as we go between slices, right? And in fact, we can show that. So we can show that, that there is a natural way of defining flux in terms of our function, a defining function P. There's also a natural choice of a space-like vector field along the boundary. I won't kind of give you the formula here, you can find it in the paper, but there's a natural choice of space-like vector field. And such that you define the charge at scribe plus to be this. And this thing plays the exact role of Bondi masses in asymptotically flat spacetimes in the sense that it has a monotonic type behavior. So if you ask how this changes as you go between slice C1 and C2, it's got a monotonic behavior that this change is always strictly negative. So again, it's a rigorously defined quantity which plays very much the role of a Bondi mass, but this is something which is computed on a time-like slice, and it's associated with a space-like vector field, but defined carefully and rigorously, and you can prove many interesting things about it. And why do you want to prove these kinds of things? Well, that's the kind of things that people prove in relativity type contexts, right? So when you talk about monotonicity formula for the Bondi masses, it's because you're trying to, understand the evolution of the space-time, understand, how the gravitational waves are passing through the space-time. Okay, so let me conclude there with a sort of a summary. So what we're doing is we're constructing wall charges associated with time-like slices in rather general asymptotically locally de Sitter cosmological spacetimes. And the statement is that the charges are independent of the time-like slice if you don't have gravitational flux present. But in the presence of the flux, we've got a formula which shows you how the Q changes between the slices. And then we use exact four-dimensional solutions to illustrate these charges and the fluxes. In terms of what to do next, there are some things which are very straightforward, such as extending to include running scalars. So that's a computational exercise, FLW spacetimes. Then there are more interesting, I think, conceptual questions. So relating the charges and fluxes to things that you'd actually measure in gravitational wave experiments. I mentioned at the beginning that Wald had been interested in charges in de Sitter contexts. So he and his collaborators have proposed certain types of memory effects which seem to use the Riemann curvature, jumps in the Riemann curvature. And it's interesting to see whether one could characterize his memory effects in terms of the charges we're working with. And then the final comment is that, throughout this talk, I have used the relationship between anti-de Sitter and de Sitter, but I've been completely agnostic about whether there is actually a dual quantum field theory to de Sitter. I'm completely agnostic because all I'm using is the actual analysis of the Einstein equation. I'm only using the gravitational side. So I'm using the insights that we got from doing analysis in anti-de Sitter spacetimes to do this in de Sitter spacetimes. I'm agnostic about whether there is a dual quantum field theory to de Sitter. However, if you are an advocate of de Sitter CFT correspondence, then I think it would be very natural to ask, what do the charges that we are defining mean in that context, right? Is there something that you could use to develop the de Sitter CFT correspondence? Are these the things that you would use to label your states in the Euclidean? It is inherently Euclidean quantum field theory. So, there are many, I think, interesting questions in that context for people developing de Sitter CFT. So let me stop there. Thank you very much.
Thanks, Marika, for this beautiful talk. And it was quite exciting new results. So since it's the first talk that we finished on time, more or less, so we can have many questions now. So please unmute and ask. Alok.
Yeah, hi. Hi, Marika. So I had a few questions. So the charges, in the end, you want to define the charges on Scribe plus, right? On the future infinity, when you have you have the C1 and the C2, and but the C1, C2 are the time-like hypersurfaces, so that the charges you are defining also depend on the past boundaries of these.
Exactly.
So then, in principle, it could happen that I could have many time-like slices which start at the same C1 plus, and go to different C1 minuses. But then, is that little counterintuitive? Like for a given C1 plus, I could have different choice of C1 minuses, and then
exactly. So it's all completely consistent basically using Stokes's theorem. So if I take one surface which goes back in the past one way, one that goes back in another way, and I think about how it's joined together, how I choose a space-like surface that joins them, then if I just manipulate my formula, I get consistent results because my Hamiltonians depend on the contributions both at the future and in the past. So the overall contribution on those two slices will not be the same in general.
I see. Okay.
Yeah, and the jump between that will be exactly accounted for by the fact that they're different slices. So yeah, it is all self-consistent. In the special cases where you don't get contributions from the past, then indeed it's independent of how you do the slices. Yeah, so it's but in general you would actually get a contribution from the past, and so if you extend from future infinity back in different ways, you'll get a different answer for your charge. Yeah.
But if I had if I had a source at R equal to 0 at some future time, and then it kind of kicks in a radiation, then I don't know if it's very precise way to say it, but we won't expect the charge in the future to depend on the reference in the past, right? I guess it depends on the boundary condition. I guess we are thinking like that.
Yes, so I think in general you would, and it does indeed come down to how your boundary conditions are being set up and so on.
Yes. Yes.
Yeah. So in a sense, the very fact that we're allowing the contributions from the past to be non-trivial
Yes.
is that we really are allowing spatial dependence, spatial variations through the space-time. And of course, those ripple out, those propagate out,
Right.
towards the future boundary, right? So
Yeah.
that these effects are linked with it. So it is all completely self-consistent once you set up your situation. Yeah.
But in your very initial slide where you had when you did just did the Wick rotation of ABS, so you had your past boundary was the horizon. So in principle, I could have put this. I could have drawn the slices also that just intersect the horizon, and my C1
Absolutely.
minus. I see. So that I could have just done everything with the horizon and scribe plus in principle also.
That's right. And if they intersect the horizon, indeed you can do that case, and it will be discussed in a longer paper. And again, you get that self-consistency. The thing that we have that I think is new relative to previous discussion by Astakar is that we simply don't assume that the contribution from the horizon is zero. It's an unreasonable assumption in general to capture the general physics. Actually, it's just over restrictive. You're just excluding sort of realistic physical situations if you do that. But everything's all self-consistent, and basically it's really Stokes' theorem. So the section I had where I'm sort of talking about the behavior of your symplectic potentials and so on, you're really using those defining properties to keep using Stokes' theorem recursively to show that these things are actually all self-consistent.
I see. Okay. Thanks. Anne, can I ask one more question?
Sure. Yeah.
So,
of course, yeah.
So, Marika, how does this fit with this new story about the lambda BMS? I mean, you did say something that when you have radiation, the vector field is not asymptotically conformable.
Yeah, I think. Yeah, so I think that's the data point is exactly the point that again in the case that one has this asymptotic structure, you should be able to use what we're doing to construct associated charges, right? If you want to use those, you could, and that's probably very interesting, and that's almost what I'm touching on in the very last point. In a situation where we really have radiation present, I think you've broken that symmetry structure, right? But first, as ever, before we break the symmetry, we understand the implications when we've got the symmetry, right?
Yeah.
And then we do the next stage of it. So I think looking at the case of the BMS absolutely is interesting to do.
Okay, thank you. Thanks a lot.
And I think your colleagues over in Kanpur, of course, are interested in these kinds of things. So while looking at this thing.
Okay. Thank you.
Okay, thank you, Marika, for the nice talk. Can I ask a few questions?
Sure, absolutely.
So about this computation of the mass for the short-shell black hole, you said that Q minus is 0. There is no contribution coming from the past. Is that what you said?
That's right. Yes. Yeah.
And the reason is that the slices that you consider, they end at the horizon of the bifurcation point at the horizon.
Well, not necessarily, but they are ending. They're ending in a sort of they're ending in the middle of the space time, and the fact that you're getting no contribution there is essentially that it's due to the fact that you don't have radiation present, etc., etc.
And in the computation you showed for the Robinson-Trotman case, how is this Q minus calculated there? The T ends, where the surface ends in the past.
Okay, so maybe let me go and share that again, because I'll just go back and show you the picture. There we go. Okay, hopefully it's gone up.
Yeah.
So if you just look at the picture here, so we're really interested here in the case. So the region or the slice that we're considering is shown in red, right? So it's actually coming down from the scribe plus, and it's just coming down, finite part. It's not crossing the horizons. I mean, one can discuss more complicated situations, but I'm not trying to make it cross the horizons. The reason I'm not doing so is because our Robinson-Trautmann solution in general is very complicated, right? So we're considering a defining function P for which we don't have an analytic solution to the Robinson-Trautmann equation. What we have is an asymptotic solution near, in the region that I'm shown here. So up here, it asymptotes to de Sitter-Schwarzschild. So P approaches the P in asymptotic, de Sitter-Schwarzschild, right? So that's the region I'm considering. And I'm considering this just to, in a sense, illustrate our computations, illustrate our analysis. If you wanted to analyze the charge structure for Robinson-Trautmann more generally, and you wanted to sort of take your boxes going over here, and sorry if I show it clearly with my line, if you're trying to show it in going into, crossing horizons and so on, I mean, that's a more complicated situation, essentially, because then you have to start analyzing the behavior of this function deep in the interior of the space-time, where you don't have an asymptotic expansion of that in terms of P is the Schwarzschild de Sitter P plus small corrections, right? There's no sense in which you've got an expansion of P. Does that help a little bit in terms of what we're doing?
I see. Okay.
Yeah.
So the contribution to Q minus is 0 in your case.
No, I should have said actually, so sorry, I should have said that. No, it's not 0. So in general, it's not 0. And we, actually getting an elegant, we've got an expression for it. I didn't put it on the slide because it's not particularly revealing. The contribution is not 0, right? So it's expressed in terms of the value of P and the derivatives of P and so on. So the actual charge gets a contribution both from Scribe plus and from the past boundary of the box. So we're showing a monotonicity behavior for delta Q plus, which is interesting in itself, but indeed the charge itself gets contributions from the past bit, in general. Yeah.
And in this example, in the Robinson-Trautmann example, the G0 is not conformally flat. It is.
Yes, exactly. So the G0 is not conformally flat, but there's a sense in which it is, you can write G0 as an expansion. So the expansion, because we're working in the region where it's becoming Schwarzschild de Sitter, we can think of it as basically, just the G0 being the G0 for de Sitter plus small corrections to that. But you're absolutely right. It's not exactly, it's not got a conformal killing factor. And that's an important thing. And again, maybe I could put more on it. That's why the vector field we're choosing, it's not a conformal killing vector, but in the case where we switch off all the radiation, it does become a conformal killing vector. Yes, in the case of Schwarzschild de Sitter, it would be the conformal killing vector, but it's not in general a conformal killing vector. So there's just a very natural choice, which had already been, of course, people have analyzed these Robinson-Trautmann, space-times for decades. It was well known that this was a particularly natural sort of vector field to look at. And that's the one that we actually use. Yeah. Okay.
Okay. And in the abstract of the talk, you mentioned you will say something about the Kerr Robinson-Trautmann and the Kerr de Sitter also. Have you?
Yes, I think so. Let me go back. I just skipped it. I skipped it a little bit fast. So, I mean, I said a little bit about, Kerr nut de Sitter, and said that actually you could, this is a case, of course, which is stationary, but that because you've now broken the rotational symmetries, you have more non-trivial charges, right? And the charges are obviously expressed in terms of the parameters. Now, in terms of, generalizing, in the next point, you can also take Robinson-Trautmann solutions which have rotational behavior, right? So again, for suitable choices of P, you can actually get, Kerr-type behavior as well. They're not shown on these slides, but in some sense that almost just comes along for the ride, I would have said. So, the conceptual stuff doesn't really change here. The Penrose diagram, of course, becomes, incredibly even more complex, but conceptually for the things that we're doing, I don't think it adds much apart from the computational complexity. And there are, when we get to the discussion here, as well as having a Bondi mass type quantity, you've got additional kind of cues associated with additional vector fields, which you can think of as kind of characterizing the sort of angular momentum type behavior. And they also have appropriate monotonicity properties for them. So yeah, it's very much analogous. So.
Okay, and one last question. So trying to connect to what Alok was asking. So what do you think, is it a natural question? Is it a valid question to ask? What is the asymptotic symmetry group in asymptotically locally de Sitter spacetime, or what is your view on this?
I think it's a very valid question. So, that's certainly something that can be analyzed. And it is going to be picked up and inherited from analytic continuations from ADS. I think the next question would be then, can you use that to infer something about a holographic correspondence? And there, I think it becomes tricky, as we see also with asymptotically flat holography attempts. So people, of course, trying to elucidate, the BMS groups and so on. But nevertheless, there are sort of substantial challenges to actually turning that into dynamics, right? So it gives you kinematic structure, but it doesn't necessarily give you enough to pin down an understanding of the dynamics of the dual theory. So definitely interesting to pursue, but it's will it answer all of the tricky questions? I'm not sure, but interesting to explore.
Okay, thank you.
So some of this, sorry, and can I just ask?
Yeah.
So some of this, the definition of the charges rely on some kind of an implicit identification of zeta plus and zeta minus, Marika? Or, I mean,
that's right. So absolutely, and maybe I should have paused a little bit more on that one. So in cases where you've got, a conformal killing vector of the boundary, it's clear what the vectors are, right? You start with the vector in the boundary and you just extend them to the bulk. And actually, there's lots of math theorems that these extensions are unique. So that's all fine.
Yeah.
In the case where you don't have a conformal killing vector, you're absolutely right that there's a subtlety about what vectors would you use. So although the constructions that we do, and I emphasized at the beginning that I wasn't assuming that something was necessarily a symmetry, it was a diffeomorphism. So your construction goes through, but you need to have something with a physical interpretation. And that's why the Robinson-Chapman is quite a nice example, because it's something where it doesn't have a symmetry, but there's a sense in which the symmetry is softly broken. Because the thing is asymptoting to something which is, Schwarzschild de Sitter, right? So there's a sense in which it's kind of relaxing and gradually sort of, becoming that, in which, that there is something which is, there's a symmetry which is softly broken. And that's the thing which gives you the natural choice of vector.
Yes.
Now, if you just gave me a random time-dependent de Sitter cosmology, where I didn't have that connection, in the sense that there wasn't a sense in which it was a relaxing, it was becoming a perturbation of de Sitter, I would maybe not have a natural choice of vector to choose. And that's, I think, something to explore.
So I have actually a related question here. So so this continuation, analytic continuation from anti-de Sitter to de Sitter, you could only do it in Pfeffman-Graham like coordinates, or you could also do it other.
Yeah. So for the asymptotic analysis, the Pfeffman-Graham approach is the most convenient, but you can, if you want to, do it in Bondi-Sachs type coordinates. And actually, Kostas and I had another paper with Aaron Poole, where we were doing asymptotic analysis in Bondi-Sachs type coordinates in ADS in de Sitter. So you can definitely do that in both.
So in general, of course, this Balasubrahmanyam-Krauss kind of approach will allow you to use any coordinate system. And so in that context, suppose if you did this Eddington-Finkelstein, like from continuation for this Robinson-Trotman, so there you could have got other kind of slices also, right? I mean, you could have defined some other natural slices.
Not so much, I think. So you can do your analysis in different coordinate systems, So if you use Bondi-Sachs type coordinate systems, you really want to foliate the space-time perhaps in terms of, you might be foliating in terms of null slices. Well, I was choosing time-like slices, but actually I could have tipped my time-like slices to be null if I wished. I could kind of take an asymptotic limit where they became null. You can do that. And in fact, if you're taking your slice on which you're defining the charge to sort of intersect a horizon, it's almost naturally sort of wanting to asymptote to something which is becoming null, in fact, at some point. So that you can do. I think the only thing I would say about choosing a particular coordinate system, I mean, in the bulk, it doesn't matter. At the boundary, it's sort of, it's most elegantly expressed in the Starobinsky, Pfefferman, Graham type coordinate systems. It's just much more complicated. The same structure of the asymptotic expansion is there. But as you can see from the paper we wrote with Aaron 2 years ago in the Bondi-Sachs, the expansions are a lot more complicated in different coordinate systems. So you're basically obscuring the simplicity, I think. This is the maximally simplistic coordinate system to use. So, yeah.
Okay, sorry, interrupted Alok.
No, that's fine, Anne. Yeah, so I just wanted to, just one more question I had. So in the lambda BMS case, there is no canonical identification. I mean, there are two lambda BMS at, I guess, Scri plus and Scri minus for the sector. So that's, I think what you're saying is that's still open to ask, is there a canonical way to identify zeta plus and zeta minus?
I think so. I agree with that. Yeah. And I should say here, actually, again, I probably underemphasized it throughout. I mean, in these discussions, we are treating Scri plus and Scri minus independently. So, it's completely logically possible to have different symmetry groups there, and so on. And that just comes in and so yeah, it's perfectly possible to have that.
Yeah. I mean, in flat space, we have this antipodal identification.
Exactly.
And we need something like that.
Exactly. And here you would, of course, get something similar happening because, ultimately, if you want a smooth space-time with, no discontinuities of geodesics, right? You are going to be able to track.
Yeah, exactly. Yeah. So maybe that's a natural way to start.
Yes. Yeah.
Thanks.
Okay.
So I have wanted to ask for something. Suppose we look at DS3. Is there some physical meaning that you could give to Bernoulli step geometries?
Possibly, yes. I mean, I think the analysis we do is in odd dimensional spacetimes, you've got the issues associated with conformal anomalies, but they're well understood. But the other conceptual things just go straight through. So absolutely, you can associate things with time-like slices. You can think about what that means. If one was going to try and connect with holographic approaches, the three-dimensional case is probably the most straightforward because it's got more underlying symmetries, right? You've got a larger symmetry group. So yeah, it isn't something I should say we particularly thought about, but
yeah, so I'm talking in the situation where your boundary metric of this G0 doesn't change, you keep it flat, but your subleading thing becomes this, yeah. So, okay, so yeah. So you're saying that this will be physically inequivalent solutions even, and they should have some meaning.
Yeah.
One more question, sorry. So Marika, for you, the gravitational radiation is non-zero symplectic flux at the boundary. Is that
yes.
Is that correct? Can one be more refined about it? What are the polarizations? Because relativists would worry more about these things, how to characterize gravitational radiation in a curved spacetime. So can you comment?
I mean, I agree with that. We do have various refinements of expressions which are going to come out in the long paper. And then these connections that say this memory effect that Wald had, which was really characterizing things in terms of components of the Riemann tensor, that's certainly something we're thinking about how to connect that. The polarization issue, that's fairly straightforward, right? I mean, it's quite easy to split it into polarizations. The connections with the Riemann tensor, you really have to translate what we're assuming in terms of the asymptotic structure, in terms of what that means for the Riemann tensor, to link it with what Bob Wald was doing. And again, that's something that's underway to do. that stuff, it's not so clear to me that they can really detect that, but at least, linking what we're doing to what he's doing and characterizing it in different ways, I guess, is the first step to sort of seeing how you can actually detect it. But polarization is, that's of course just straightforward to do, right? Because you just project it down onto the different pieces.
Okay, thanks.
Okay, so I think it's we already had quite a few questions, and it's lunchtime for you. So
actually, we have an India week at the university with lots of sort of celebrations and events with the commissioners from India, and we've got government ministers. So I'm going over this afternoon to talk there, but obviously not about physics. I'm just presenting the work of the math department in general. Some of our colleagues have been involved with LIGO India, although that seems to be sort of on hold, right?
Some of my colleagues here also in the center were part of LIGO India.
Yeah. But from the university perspective, I just want to throw in the sort of the fundamental science side, right? Because a lot of the presentations are very much about immediate applications, right? So it's good to sort of see that, it's good to showcase the sort of fundamental science as well.
Oh, very good. Yeah. No, in India, we have a big community, of course, and students. And
yes. And it's interesting because we've got various partnerships with, again, the people who are trying to promote trade relations between Britain and India and so on. And I keep saying when I go to these meetings, but the Indian science community is fantastic.
Sorry to interrupt. I just stopping the record.
Okay. Yeah.